Welcome to this presentation on data analysis using SNOMED CT. The presenter is Sander Mertens from Ttest in the Netherlands. My name's Ian Green. I'll be the moderator for this session. I'm the Customer Relations Lead for Europe and the Clinical Engagement Business Manager. And without further ado, I'll hand over to Sander.
Well, hi everyone. Thank you for the introduction, Ian. And thanks for the chance to show a little bit of my work today. As Ian said, my name is Sander Mertens. I'm working at the Dutch SNOMED National Release Center as a terminologist for about a year now. I mainly focus on mapping and implementation of terminology in daily practice. So I work with hospitals and analysis consulting firms. And before my current job, I worked as a medical doctor in hospitals, more specifically as a surgical resident. And as a side project during that time, I started working on my PhD in upper GI surgery, which might explain my fascination with data analysis. And I'm working on the finishing touches of that PhD and get more and more amazed at the potential of semantic interoperability. And of course, mainly the part that has yet to be implemented in hospitals. I will first go into the basics of SNOMED CT, after which I will explain what the current issue is with data retrieval and the basics of how terminology can assist researchers and analysts. I will show how Snowstorm can be of service and show you a little bit of the advantages of graph databases. A SNOMED concept can be represented in a graphical manner, as shown in the slide, and the concept in question is chronic pulmonary embolism, which is a pulmonary embolism and is a chronic disease of the cardiovascular system. In the hierarchy of SNOMED, these are parent-child relationships, and apart from these ISA relationships, several attributes are shown that further provide some metadata to the concept. There's a clinical course, a chronic clinical course, looks like an embolism, and it is found in the pulmonary artery. And this view is very useful to humans to understand the concept, but computers are at a loss. The way the SNOMED International browser displays this information is by using several blocks. The parents at the top, these are broader than. Children at the bottom, those are narrower than or more specific. And of course the attributes. But this exact same information can be exchanged as an expression. And this confusing bit of text carries the same information, but is easily understood by computers. And every SNOMED concept can be written in this manner. If you link all SNOMED concepts together using the parent-child relationships I showed earlier, you will end up with a hierarchical tree such as this one. Most of you will know this, but one of the more unique parts of SNOMED is that a concept can have multiple parent relationships. And if one of these circles, for example, represents a concept like appendicitis, a child concept could be, for example, appendicitis with a perforation. Now, as I said at the beginning, I'm a PhD student working with clinical data, and a lot of my time, therefore, was spent filling up spreadsheets such as this one. And if you want to research a subject in clinical context, you ask the administrator of the hospital to give you a list of all the patients that were, in my case, billed with a certain code. And this code is often extremely imprecise, such as abdominal wall hernia or something as broad as that. What part of the abdominal wall is unknown. This meant in my case I had to go through over 5,000 patients to find the 300 that I wanted to study by looking at every doctor's note, every reason for all of these patients. I would then fill the last column with the diagnosis of the patient for further analysis and data retrieval for the patients that I want to include in my study. The data on screen is generated using Cynthia, which is an open source package for generating realistic looking clinical data. And I will have a link for you at the end of my presentation. And this provides you with a list of patients shown on screen, but also with a table for visits, medication, procedures, measurements, conditions recorded for the patients, etc. Now, if all 5,000 of my patients would have terminology-coded diagnoses, my spreadsheet I got from the administrator could have looked like this. Column E in this case contains SNOMED IDs for the condition or disorder that the patient has, along with a start and stop time, if applicable, and the encounter that this diagnosis was registered in. So we can also look up the measurements made at that time. Now, if we go back to the SNOMED hierarchy, and we would take, for example, abdominal wall hernia, that could be the highlighted circle. All disorders that are more specific should be lower in this tree. We can use this hierarchy to make a list of SNOMED IDs that are related to our research question. An even more interesting use case of SNOMED, using SNOMED for selecting of patients, is selecting SNOMED concepts based on their attributes. We could, for example, select all SNOMED concepts that are defined with an inflammatory morphology found in the nasal sinus. This could lead to a selection of disorders all over the SNOMED hierarchy, represented in this case by the filled-in circles. We don't have to rely on parent-child relationships for this selection, but can make a much more refined filter in the SNOMED catalog. If we select all SNOMED concepts defined as inflammation of the upper airways, and note down all the SNOMED IDs that fulfill that criterion, we could filter our spreadsheet on these numbers. That would leave us with only the rows marked with a green ID in column E. When I first thought of this, I found it incredibly useful, but also extremely time-consuming, since this could be an enormous amount of SNOMED IDs. Luckily, we can find those SNOMED IDs in an automated way by using the SNOMED expression constraint language, ECL for short. This is a simple query language, relatively. I have an URL to the specifications at the end that allows you to query the SNOMED terminology server with this kind of question. And while there are a few terminology servers out there that support ECL, the SNOMED International, for example, provides the open source terminology server Snowstorm for free. There's a REST interface and a small web page that allows you to enter just your query in text boxes. I won't go into too much detail here due to time constraints. But if you ask the server a question, the response could look like this. This is a JSON object, which is standardized, easily readable by a computer. And in this case, I queried the server for all concepts that are descendants, or more specific than, appendicitis, which returns a list of SNOMED concepts that fulfill that criterion. We could use this to filter our spreadsheet. Now, to some practical examples. I'm used to perform my statistical analysis with the open source package R, and I will show you some simple examples of analyses that can combine the power of both packages. Now, R doesn't have any understanding of Snowstorm or SNOMED, so we will first need to write some functions that allow these two software packages to interact. We need a way to search in the description of concepts, and a function that allows us to use these ECL queries. I will not focus too much on the code, but I will show some excerpts and explain what they do. We'll just name our function, tell it where to find the Snowstorm server, what variables to use for our query, and how to edit the data so R can work with it. In the end, it produces a URL, which sends a request to the server, and you can handle the response. All of the code that I show you here today will, of course, be available on request. If we use this function for searching in descriptions that we created before, and we tell it to search for lower extremity in SNOMED, an enormous list of concepts will be retrieved. We have body structures, disorders, therapies, etc. This is not very efficient or a reliable way to find the right concepts for your conditions filter. A ECL query is way more useful. On the top you can see some code within red the ECL query. The first line uses the smaller than signs. Two of these in a row mean descendants of the SNOMED ID or the ID itself, and everything between vertical lines will be ignored. So we will get the concept disease and all concepts more specific than disease, so basically all diseases in SNOMED. This, again, amounts to a huge amount of concepts, so we need to further specify what we need. The colon indicates further specification. And after the colon, we specify that we only want diseases that have the associated morphology damage. And we also added the less than signs next to damage, so we will also get concepts defined with subtypes of damage, like, for example, infarctions. Below the code, you can see the results of this query. It includes everything from a fracture of the mastoid down to something very specific, such as a blowout fracture of the left orbital floor. We can take all these SNOMED IDs on the left and apply those as a filter to our spreadsheet. After filtering and counting the conditions that we are left with, we end up with the table on the left. We have records of patients with bullet wounds, hip fractures, burn wounds, all kinds of damage. These diagnoses are fairly broad, and this is caused by the fact that Cynthia uses ICD-10 coded data to generate the conditions table. And ICD-10 does not get much more specific, and this limits the amount of detail in your data set. This is another advantage to coding your clinical data with terminology instead of classification. We can also display the data as a nice graph for the head of the department. An even more specific example could be looking for all diseases that involve acute infarction of the heart, for example. This includes all kinds of infarctions, with or without ST elevation, and of course you can get as specific as you like. But of course, hold in mind that it is also possible to get too specific. Now for a more realistic analysis, I would like to see if there is a difference in the mean body mass index of patients with or without diabetes. This is not a very valid research question in itself, but then again, this data isn't either. It will, however, serve as a good example of what you could do with your real patient data. First, we will create a list of all types of diabetes using an ECL query. You can see in the table that this includes, for example, neuropathy due to diabetes type 2, gestational diabetes, diabetes due to pancreatic injury. These patients would normally not be in the same database and definitely not using the same method of coding. The oncologist would have some of these patients in their audit database. The nephrologist would have another fraction. But using this method, you could realistically select them from all of those databases. Now, this is an interesting looking piece of code. Don't look at it too hard. It will go through each individual patient, see if they have any recorded diseases, see if any of those diseases are in the list of types of diabetes that we just created. And then it will add a column to the spreadsheet with a 0 for no diabetes or a 1 if the patient has or had the diabetes. They also prepared an average BMI for each patient based on all the measurements in the database. And this is, of course, a simplified analysis since we are not checking if the diagnosis is recent, still active. We also don't know who added the diagnosis. And these checks are, of course, relatively easy to implement, but due to the short time available for this talk, I won't leave this to your imagination. Now, with the ones and zeros added to the patients, we can plot this in a box plot. As an overlay, I added all the patients as a very small black dot. And visually, it's easy to see that the patients in our database with diabetes have a higher average BMI. Just as easily, we can task R with performing a Ttest, which shows that there is a statistical difference between our two groups. So now it's just a matter of the statistics, but the patient selection is basically already done. Leaving this code behind, I would like to show you one more thing. As I explained earlier, SNOMED is mainly a database of connections between concepts, and this is basically the description of a graph database. And graph databases consist of nodes and relationships. For example, here you see a graphical interpretation of a graph database, and here you see the concept of appendicitis as a blue dot on the screen. And this represents the concept with all its relationships, descriptions, and all other defining characteristics. Even though this might look like the coronavirus, it is not. It is using the query language of Neo4j, which is the package I show you on the screen, link at the end. I asked the software to display all patients that have a relationship with appendicitis. Each orange circle is a patient. The green lines are relationships of the type has condition. So basically what you can see here is all these patients with shown in orange have this condition, appendicitis. In this screen, I have expanded the view a bit further. We see some patients in orange, green lines to SNOMED concepts, has condition relationships, but also you can see some lines from concept to concept. And in this graph, I have queried a database to show me a number of patients, their recorded diseases, along with the path of relationships that you would need to traverse the SNOMED hierarchy to the concept disease. The blue SNOMED concepts on the screen are linked by their ISA or parent-child relationships. This kind of database can be used in the same way as a traditional database, like my first example, but it has additional advantages. Since graph databases are optimized for relationships between entities, it can be used to quickly visualize these connections close to real time. They're used a lot in crime analysis, but disease analysis is a very real possibility. You can visualize these connections close to real time. In this screen capture, you can see that there is a group of patients on the left that have disease A, on the right a group of patients that have disease B, and in the middle you can see a large group of patients that have both diseases. You can imagine how useful this can be on a large scale to identify correlations between clinical factors. The very last example, this is shown in this little patient cohort. On the screen it shows all patients in my database that are younger than 30 years old and live in one specific city. Not a lot of patients, 25. And by showing the relationships between these patients, it becomes obvious that all of these patients, apart from 2, have experienced some form of upper airway or ear infection. And this might help identify clusters in a population. If you perform this kind of analysis on an entire population, you might find connections that you would never have thought to look for. This can then be used to form a hypothesis for further research. That's all I have for you today. If you want access to any of the code I showed here today or would like to have further conversation, send me a question through the Q&A interface or send me an email. Thanks for your attention.
So I'd like to thank Sanders for the presentation, and we're going to move now from the recording to a live Q&A. So thank you, and as Sanders said, please put your questions in the Q&A box. Thank you. Hi, my name's Ian Green from SNOMED International. I'd like to welcome you to this live Q&A session. I'd like to thank Sander for his presentation. I'm sure you all found it very informative. We've been gathering some questions during the presentation, and I see that more of you are putting questions in as I'm speaking. So let's start with trying to address some of these. So Sander, would you be able to share the script, the R script that you're using, that you referred to during your presentation, to help people?
Well, that's a very easy question. Yes, of course. I have spent some time creating a script that at least is able to interface with Snowstorm. It could be expanded upon, of course, but as a source of inspiration, for sure. Just send me your email address, maybe you can do it in the Q&A as it is private, or send me an email through the email address shown on the first slide.
Okay, and keeping on the R theme, are there any R libraries that deal with SNOMED specifically?
Not as far as I'm aware of. It's not a very often used combination, of course. But on the other hand, Snowstorm is available as a general API, and R is able to interface with basically any API over the web libraries. So it's very easy to program it yourself. And in my example code, I can show you this.
Okay, and can you kindly repeat the name of the tool for DataViz?
I'm assuming this is a question about the graph database that I showed. This is Neo4j. I also have a link to that in the on the last slide. It's basically a graph database, and they also provide the software to interface with it on your desktop. It's there's a community edition freely available, and there are enterprise editions that scale up to enormous levels of data. Okay,
a nice simple question. Is the data in this presentation actual patient data?
Interesting question. Yes and no. As I said, it's generated by Synfia, which is an open source package, also a link on the last slide. It generates patient data based on ICD-10 reported incidents. So it is based on actual data, but it's not like you have real patients in your database. You can use it to create analysis and demonstrations such as these.
Okay, and what are some good free example data sets?
I think, again, Synfia is very good for this, as it gives you a database, multiple tables, basically a database, including everything from measurements such as blood pressure, glucose levels in the blood, patient visits, personnel details such as addresses, everything you would need to simulate a real database.
Mm-hmm. And were the links that you talked about between patients and diseases, were they explicit or inferred? And if they're inferred, how was the inference done?
Sorry, could you repeat the question?
So were the links between patients and diseases explicit or inferred?
In the database that I used, I think this is the question at least, there is a relationship between patients and diseases. It says when the diagnosis was made, by who, in which doctor's visit. So in that sense, I think it's implicit. Yeah,
I'd agree. So I have a comment for you and a question that goes along with it. So the graph database solution is interesting, but there were less than 200 nodes on the graph. Does this solution scale well? And if it does, what are the limits?
The solution that I used in this case, which is the consumer edition, free edition of Neo4j, doesn't scale that well. If you try to show over 1,000 nodes on your screen, you run into issues. But that's using the community edition. If you use the also available, got the name, I think it's Bloom interface, this is able to generate to show a large amount of data. It's also used in, as I said in my presentation, crime analysis, for example. It's able to show relationships between people on a national scale. What you could also do to get this a bit more performant is aggregate patients that have the same relationships, for example. It takes a little bit more coding, but it's easily done. And this tool is meant for visualizing large amount of data. So it does scale, but it does take some effort.
Okay. The next one is not a question, it's more a statement, but SNOLIZE is on GitHub.
I would have to look into that.
Have a look at that. Is using the Snowstorm API, I know the answer to this, but I'll ask you the question anyway. Is Snowstorm API free to use for everybody? And could this person use it as an example to build an app?
But I think of course, you know the answer. I know the answer. It is free. It's maintained by SNOMED International, a group of very dedicated developers. This is a fact that I also like to tell to everyone that asks me questions about Snowstorm. If there is any issue with the Snowstorm engine, the team is very quick to respond, and I have received bug fixes within 10 minutes before. So I would encourage you to look into that.
Okay, I don't guarantee those service levels going forward. We're good, but we're not necessarily that good. Did you use the Snowstorm Fire API or the Snowstorm native API?
In this case, I used the native API.
Okay. And how are the SNOMED codes at your location stored? Are they stored as Fire, JSON, or something else? Does R code search within that structure?
Yeah. In my database, well, I used Synfia, which creates CSV files. So that's basically just tabulated data. And I imported it into a data frame in R, which is how R stores all its data, basically. And R handles all the searching and filtering.
Okay. So that's the end of the questions submitted by the audience. I have one which I tend to ask presenters such as yourselves. If someone was going to start off on this journey and look at creating cohorts, where would you start? What would be your starting point? So what was your starting point?
That's an interesting and very broad question.
It's a broad question, deliberately so.
Yeah. The first thing that you need to do if you want to do anything, any meaningful research, is of course define your question. As I said in my presentation, this is a very crude example, but if you would try to analyze a real cohort of patients, you would need some extra metadata from every measurement, every diagnosis. Since in this case, I did not check, for example, if a diagnosis was recent, if it was debunked, if a blood pressure was measured during a time of stress, for example. In the Netherlands, we try to structurize all the data storage by using clinical building blocks so that everyone stores the same thing. So next to a diagnosis, you store who recorded the diagnosis, if it's recent, if it's merely a suggestion. Yeah, garbage in, garbage out is the standard sentence used in any talk about data analysis, and I think it very much applies here. Get your data right. That's, I think, the place you should start.
Excellent, and that's the answer I expected. So I have one, it's not a question, one comment from the internal staff. So the Snowstorm software is free for everyone. The public API instance, which runs the browser, is only for casual use and testing. It's not for production applications. If you're looking at using that for production, we'd expect you to host your own, and the code's available on GitHub to do that. Right, so looking at the time, if we have no other questions, so I'll count to 10. If any other questions from the audience. Otherwise, I'd like to thank Sander again. So thank him for his presentation and also for answering all the questions. And thank you, the audience, for attending. And hopefully you'll enjoy the rest of the expo and other presentations. But thank you.
Thank you for your attention, and please send me an email if you want code or have any other questions. Thank you.